Cool. Okay, welcome everyone to week 21 of Intro to Quantum Computing. This week we are going to be implementing Grover's algorithm in Qiskit. Um, yeah, sorry for being more of a mess than usual. I've been having computer issues for some reason. Um, yeah, so today I'll get started with the attendance quiz passcode is as usual in the bottom right-hand corner of the screen. And we'll have like the usual program. Um, we are at much lower capacity than usual. So I'm not sure why that is. I know it's some people's spring breaks, but yeah, so to get started with that also, next week and the week after, so the next 2 weeks actually, will be spring break for qubit by qubit. So you will not need to attend anything for the next 2 weeks. So that includes lecture, lab, and homework as well. Like there's no homeworks that will be assigned. However, we will be giving out certificates for passing the course. So if you want to have your name correct on your certificate, please submit your name for how you'd like to see it printed on that certificate. And that is the only homework that you have for spring break. So we're not giving you like a big project to do during your break time. Yeah, so that we also have our attendance quiz as usual. This week is which topics from the semester would be most helpful to review. We do plan on doing a review session at some point. So we will we will have the opportunity to review material that you're maybe less familiar with or we went through more quickly. I know specifically the Deutsch-Jozsa algorithm. We think the people in charge of making the curriculum and the TAs think we went through it a little bit faster than we would in future years, just because it is the first quantum algorithm and it is not particularly trivial. So that is like one thing we're thinking of doing more on. Another is also actually all the TAs do research in the field, and so we could go through some more hardware implementations or more research specific topics. Of course, the material covered would vary depending on what TA you have, but that is also something we are considering doing. So definitely let us know what you are most interested in hearing more on. Gotten a question from Stereo. Why is there no homework this week? Grover's algorithm is an important topic. I mean, we don't have homework because of spring break. I don't know if we're going to be doing a makeup homework that touches on Grover's algorithm. I will say, the math for Grover's algorithm is substantially more involved than any of the other math you've had to do in this course. It's not complicated, really, but you have to take a bunch of tensor products and then multiply together a bunch of 4x4 matrices. Or alternatively, you could create an algorithm to factor the unitary for Grover's diffusion operator. But both of those things are pretty not complicated. The factoring would either be an algorithm that you found or more of an undergraduate level problem because it would require knowledge of substantial coding. But yeah, there's we might have some touching on Grover's algorithm, but I will say the material that's covered in these final few weeks of the course is substantially more not just advanced, but it doesn't have a clear simplification that is quantitative. So For example, previously in the course when we covered physics topics, we could use only a single qubit and work in a truncated Hilbert space that reduced the amount of math you had to do a lot. But with a lot of these algorithms, there's not like a really clear um, simplification. And doing the math for a lot of these algorithms is like quite substantial, and normally wouldn't be covered honestly until like a graduate level course at a lot of universities. So that you might notice a difference in the problem sets, the homeworks, because of that. Cool. And I will start the pre-lab Zoom feedback as usual.
It's on now.
Here, hello? I heard a noise. Maybe it was nothing. Okay. Yeah, and also if you have any questions about this week's material or last week's material or anything, I do like to try to answer them at the beginning, just because I know it's like a lot to process the material, like over the course of the lab. It looks like I'm seeing a lot of like 3s and 4s. Today, like I'd say like half and half 3s and 4s, and then a few 5s and a couple 1s. So hopefully we can make some things clear. I know Amir's lecture overall gave a pretty high level description and then went really, really deep into the math at one point for like 5 slides. So hopefully we can make the math a little bit more clear. I know it used a lot of bracket notation that maybe isn't as familiar. So for this, we're going to be using matrices rather than bracket notation to give you a more explicit, I guess a more mathematical computer science derivation rather, or not, it's not really a full derivation, but like a computer science like example rather than a more physics example, because it is at the intersection of both. But yeah, so we did have some questions from last week about the role of the oracle. So the oracle in general just implements a function using quantum gates, and uniquely with the Deutsch-Jozsa, oh, that's a little bit unattractive of a line. Let me make a nicer line. The Deutsch-Jozsa oracle will implement one or the other of these functions. It's not going to implement both. And it could be like random, like you can randomize which one you implement. So that is different from how Grover's algorithm uses oracles. In Grover's algorithm, it will always implement this one function that returns -1 for one state and +1 for all other states. And that's kind of like the prep search step. That I think was the math covered more explicitly in Amir's lecture. And so we're going to try to sidestep the oracle step again, just because the intricacies of how an oracle operates is a little bit more complicated or in the weeds than most of the material covered in the course. And one thing we'd like to note just in general is that oracle development is an active area of research in computer science. So I do not do computer science personally. I am much more on the physics side of quantum information. So I do not have like a ton. I have experience using oracles. I've never created an oracle, and I never expect to create an oracle personally. So I wouldn't be too concerned by like not fully understanding how you get to the point of this oracle. A lot of these things are kind of discovered by necessity. If you think about it for like 1,000 hours, you will eventually reach the conclusion just by guessing almost. But obviously you're just inferring everything you've put together. But it's similar to all of the experiments that we read about in textbooks. We don't have to physically implement them ourselves to know that they work. enough scientists have implemented these experiments and seen that they work in the way that we expect, so we don't re-implement them every time. Um, and you might say you stand on the shoulders of giants, and these giants in this case have created some oracles that we do not have to create ourselves. So with that, um, like to note that we do not, one important thing about oracles, and I think the only really important thing to get about oracles is that you can't look at the oracle. Um, you can't see what this function is. We do, in fact, know which function we're implementing for these oracles. However, the whole point of an oracle in like a computer science, like mathematical proof, is that it doesn't matter what's inside it. All that matters is what goes in and what comes out. And that's not always the case for other things. And so this is kind of this is a unique caveat that is important for like advanced mathematical proofs, but you also don't have to like you don't have to prove to yourself that the oracle could be anything that does the same inputs and outputs. But that is an important aspect of oracles. Um, so this is just repeating what I just said. Um, Similarly, our algorithm in in the case of like one metric of complexity is the number of queries we need to figure out this particular oracle function. So the oracle can do something to set things in the right way. So we've put in something, we've gotten out what we want, but we don't actually know what the oracle like we don't actually know what the function the oracle is implementing actually is necessarily. You know what the unitary is. However, um, particularly in quantum mechanical like implementations, um, you are using interference effects with your actual state and your actual like operator that your oracle is implementing. Um, so like figuring out what has gone in is kind of the important part of completing the Grover's algorithm. So with that, I think that was a bit rambling. Hopefully it made some sense. We're going to try to define a lot of the terms used again. I've also gotten a question from Tomas if there's a systematic way to find oracles. So that is actually also an active area of research. One of my friends works in computer science at MIT doing actually classical algorithm development. And that is something that he does work on is like automating these kinds of proof demonstrations. So like with the way that most computer science research actually goes is you don't program anything, not anything, but you're not just like running an algorithm you've come up with on like massive data sets. If you're doing like computer science theory, you're actually just doing a bunch of math and you're writing proofs that show mathematically how your algorithm works. And you can write scripts to automate the testing of these proofs for different cases. Um, so there is like some amount of automation that can be done, but that is very much an active area of research. And kind of, I think like people do it, but it is like a newer area of the field, actually. I know like previously, he was like, my friend was previously like a pure mathematician, um, but he had never really programmed before starting graduate school. So I think there is a bit of a barrier in between like the more mathematician type computer scientists that do these proofs and develop these new algorithms and the more like application side computer scientists that are using computers to do new things and kind of more applying these algorithms that have been developed for a general case to specific cases. Cool. So with that, we're going to spend a lot of this lab actually going through Grover's algorithm. in a more like matrix-based implementation. And then at the end, we'll go through actually coding the algorithm. And we're going to show you this circuit as well, which I don't believe it was, at least was not explained. I think it was flashed briefly in lecture. And we're going to do all this for just 2 qubits, but we do have a Python notebook for this week that has a 3 qubit kind of like challenge example at the end. And then if we have time, and because this is a recorded section, I'll be going through a little bit more on oracles at the end. So with that, Grover's algorithm is a kind of unique algorithm because it offers an advantage for search in an unstructured list. And this is very, very important. This means that there is no ordering to the list. You can't break it into different parts because there is like a flag for some component of it that you can check and see like, I'm only looking for positive numbers, and your positive numbers are all stored in one place and your negative numbers are all stored in another place. This is a completely unstructured list. And so you have no idea what the data is. So for now, our best option for that is linear search, which is an O of n problem. Grover's algorithm is O of square root n, which is actually a big deal. I believe it is the fastest search algorithm, quantum search algorithm. And you really don't have any options for classical algorithms when you have no idea what your data is. You kind of have to just check every single thing and see what happens. If you're using a classical like digital computer, there are like search type things that you can do with analog computers, but they don't really exist. Like that's also an area of research, and it's very closely related to quantum computers. So you really have no other options than Grover's algorithm if you're trying to search an unstructured list and you want to do it faster. So this quadratic speedup is still a big deal, even though it's nowhere near as big as the speedup for the Deutsch-Jozsa algorithm. Which, does anyone remember what that speedup was? You can say like the O's for like your linear, or not your classical comparison versus your Deutsch-Jozsa, if you recall it, in whatever form you prefer. Thank you, Austin. I have gotten 1 answer from Austin. See if anyone else recalls. Thank you, Tomas. I'm happy to get 2. You guys are both right on, and I like that you both wrote it in very different ways. That is much more fun. Or that's slightly off, actually, for Tomas. It's O, I think you just inverted the 2. It's O to 2 to the n for the classical Deutsch-Jozsa problem, and then O of 1. Oop. But yeah, I believe that was just inverted because it is very close to the same thing. O of 1 for the quantum. And this is why we say we have our exponential speedup again in all of the news articles. This is what people like to note because this is an exponential term, and this is obviously constant. So it's kind of hard to read. So we are getting an exponential speedup between these 2. But yeah, so this might be a little bit disappointing going from O of n to O of square root n is just a quadratic speedup, but it does really scale quite well when you get to very large list sizes. I guess like, for example, like even if for a fairly small number, like if n is 64, if you go to square root n, you're only doing 8 comparisons rather than 64 comparisons, and that's a lot simpler. And it gets more and more as you go to larger numbers. So if you're searching a very large database, it could go from like days to hours for the search. So this is a check, I guess, that you can do for 10,000 entries with linear search. How many comparisons would you have to do? So like n in this case is 10,000. Can anyone give me the number of comparisons for both classical and Grover search? Thank you. Elon and Surya, you guys are both right on. So for classical, we have our 10,000 comparisons, so that's just n. For quantum, we then have square root of 10,000, which is 100. So that is a substantial speed up. That is very, very notable to try to get from thousands and thousands and thousands of comparisons, just 100. Like if you were writing out this algorithm for some reason, you're writing out each step, like writing out 100 steps might only take you like an hour, while 10,000 would take just forever. So the steps for Grover's algorithm first puts everything into a superposition state and then interferes them through a combination of an oracle and then what's called a Grover's diffusion operator. And we'll go into what each of those are. So the Hadamard, we use Hadamard gates to create these superpositions. If you remember, the Hadamard gate just looks like this. And the form is 1, 1, 1, minus 1 normalized by square root 2. We then apply the oracle to all qubits and then apply Grover's diffusion operator, which gives us an interference effect between the qubits. And so this is one iteration of Grover's search. This is not like a multi-step process. This is all in like your for loop. And then at the end, you measure all the qubits. So this here is your state prep. So this is like outside of your loop. And this is your measure. Sorry, I'm writing so ugly today. I'm sorry if you can't read things as well. I will try to be better with it. I don't know what's up with my hand. And then here, this would be our for loop, is only step 2. So we actually will do this step multiple times to try to optimize for it in a like 3+ qubit search algorithm. But in this case, we are only using 2 qubits. And so we actually only need to do it once. So to give our 2 qubit example, we can, because 2 qubits gives us 4 possible states, because 2 raised to the 2 is 4. We have actually 4 characters that we can work with. And in this case, we'll assume that Waldo is the 4th in the list of the characters. If you're 1 indexing, obviously he is 3rd. If you are 0 indexing, and we will be like 0 indexing for our quantum states. Sorry for just like zooming. Oh my gosh, I just keep zooming in. So that's what we want to do later with the algorithm. But for now, we're just identifying Waldo. To represent these 4 characters, we'll be using our 4 different 2 qubit states, so 0, 0, our 0, 1, our 1, 0, and our 1, 1, which should be familiar from all the quantum protocols we did. So and like I said, with 2 qubits, we do only need to go through our for loop a single time. With more qubits, like larger databases, we would have to repeat the second step until the probability of measuring the right result is maximized. So we'd have to keep doing it, and this ends up being square root n times for these larger numbers. So in this step, in the first step, we're going to just apply our Hadamard gates, which is going to create our superposition for all of our qubits individually. So this is not a 2-qubit gate. This is just 2 separate Hadamard gates. And this will give us an equal probability amplitude for all possible states. But what this is saying is we have no preferential start. If you somehow have some information about where Waldo might be, you can weight your algorithm differently. And that is also an active area of research, figuring out how to most efficiently weight your probabilities so you can go there in fewer steps. But for now, we have no clue. It's completely unstructured. Our problem means that everything is 50-50. This is 50% in the 0 state and 50% in the 1 state for both of these. And so that ends up being like 25% for 0, 0, 0, 1, 1, 0, and 1, 1. So this is how we might write that. This would be our 25% marker. And Waldo is noted in green, but obviously we are not, we have no idea that he is there yet. As far as we know, everything is just like in grayscale and everything is equal probability. So the first step is to write the state vector for the state Q1, Q0 after a Hadamard gate is applied to both qubits. And we'll assume in this case that both qubits start out in the 0 state. So that is like Q1 is equal to, or that's 2, 1, 0. There we go. And Q0 is equal to 1, 0. And what we're going to do is we can take the like combined 2-qubit state for these. So if we say this is in the 0, 0 state, this Q1, Q0 that we're starting with, let me put this in like a little bras and kets, would just be 1, 0, 0, 0. So we are 100% in the 0, 0 state. So this is 0, 0, this is 0, 1, this is 1, 0, and this is 1, 1. Similarly here, this is 0, this is 1. This is 0, this is 1. So to denote our basis. We now want to apply a Hadamard gate to both qubits, and you could either do it by taking the tensor product of these 2 Hadamard gates and make it into a larger matrix, which I can show you how to do, or we can just apply the gates to each qubit individually. So I guess before I do the slightly more annoying, but maybe, but will be very useful math in a second, what would you guys guess is the state vector after we've applied a Hadamard gate to both qubits? Okay, I'm not getting any guesses. I can start working through the math though. So our Hadamard gate is, there are no zeros in the Hadamard gate. I'm actually gonna write these smaller also because I realized I'm going to be a little tight on space. So it's going to be 1, 1, 1, minus 1, normalized by square root 2. We're going to take tensor product of 1, 1, 1, minus 1, normalized by square root 2. And then this tensor product, you kind of multiply each, like you're going to multiply first this guy by this whole matrix. So I'll make a bigger matrix. I'll just multiply these factors first. This gives you a 1/2 outside. And then I'll make a really big matrix. So we're going to multiply 1 times 1, 1, 1, and -1, and just populate that. So it goes 1, 1, 1, -1 up in this top quadrant. Just like a kind of block multiplication we can do. Then use this guy. And this is going to be in this quadrant. So we multiply this guy by this whole matrix to get you this quadrant. And I'll remove my circle so that it's not as ugly. 1, 1, 1, -1. We'll then multiply this guy by the whole matrix again. 1, 1, 1, -1. And then multiply this last one. So this is our -1 by this whole matrix. And this will give you -1, -1, -1, 1. And then we can multiply this whole thing by our 1, 0, 0 state and get our answer. And I somehow did this right. I was like, I'm going to mess up this, and you guys are all going to be like, wow, she doesn't know how to do math. But I do know how to do math sometimes. So what we're going to write this out as is I'll do like this as, oops, I'm on eraser mode, Hadamard, tensor product Hadamards. This is how you make a 2-qubit state. And then you apply this to our Q1, Q0 vector. So this is like your whole matrix guy right here. You just multiply them. And so you're just actually multiplying right down this column. And so this just gives you 1/2, 1, 1, 1, 1. Yay, everything has 1/2 probability. Does anyone know why it's a 1/2 probability amplitude? I've noted it, so hopefully that gives you a hint. Why is it 1/2? I thought we had 4 options. Oh no. You guys are great. You guys are so quick. Okay. Yeah, thank you, Jade and Adam and Carmen and Angela and Fahim and Elon and Sarah. You guys all got it right on. So this down here is actually square root n. So the number of qubits or the number of states we have. We could also write it as like square root n squared, I guess. Or no, it shouldn't be square root n squared because we have square. It could be also written as square root 2 to the n, if you're into that. So this is 1 over square root 4, which is just equal to 1/2. So that's why we get that normalized state. This is how you do some basic tensor math. It looks really ugly and difficult, but if you just remember that this whole quadrant, actually let me try to do color coding so it's like really easy to tell what happens. This whole thing up here is just this guy multiplied by this matrix. This whole quadrant is just this guy multiplied by this matrix. This guy is this one multiplied by this matrix, or this one is this one multiplied by this matrix. And this one, no, this one, no, I'm writing it backwards now, is this one, like I said, multiplied by this matrix. And so it's actually like pretty straightforward to do this. It just gets really ugly and difficult as we get to larger matrices. And then all we have to do is multiply it by our initial state. And then we get our superposition of all of our qubits. And you can see how it all works. And it's like surprisingly straightforward, even though it seems like all quantum and magical. I did the math right. I can prove it. This is the state we get. It's equal probability for every state. And the probability for every state is 25%. And this does mean we don't know which of the 4 characters Waldo is. So now that we've prepared our state, we need to start moving towards our goal. What is our goal in this case? Well, we would like our state vector to be 1, where Waldo is. And then we want it to be 0 everywhere else. So that means we have 100% Waldo. So that's always our goal in life, to be the most Waldo we can be. So the mechanism we're going to use to get there is called amplitude amplification. And so what that means is we're going to perform operations that will slowly increase the amplitude of Waldo's state and decrease the amplitude of all the other states. And we can do that because of the interference properties inherent in quantum mechanics. So you're given kind of an example of that in lecture, and we're going to do a slightly different example today. So if Waldo was in the 4th position, we would like to end up at this state at the end of the algorithm, where this is, oh, there's no zeros there. This is our 1, 1 state. So the second step is where no one likes this part because it's the oracle part, but it is important. But we're just going to put it in its little box and not deal with it. And you can prove to yourself how the oracle gives you what you want, but kind of solving the inverse problem is much harder. You might call it NP hard. And I think it is actually NP hard. The inverse problem is a lot harder than the initial problem, especially for many qubits. But in this case, what do we want the oracle to do? Well, we want to amplify Waldo's position. And the first step to amplifying his position is actually inverting his position. And this is kind of our magical quantum part of the algorithm. So the oracle is super, super important, but also it doesn't matter exactly how he operates, so long as he operates and does this. So this is like the quantum mechanical portion, or the more quantum mechanical portion of the algorithm. The interference effects, I guess, are also quite quantum mechanical, and you get the superposition that helps you out a bit. These aren't many qubit states that you're dealing with for the most part. They're 2 qubit states. And for this to work, you do need to be able to flip your probability amplitude. So if you remember in lecture, we had like our little state vector graph where we have our Waldo state. We have our all minus Waldo state. And then we had our all state. All state. But what we're doing for this first step is we are flipping it right over the all minus Waldo state vector and giving you this like second state, which I guess, I don't know what to label it, like second state. This is here. And we're starting in the all state. So that's what the oracle is going to do. And to choose what we want, like how we want this oracle to work, we're going to flip the sign of the state. We're going to flip the sign of the state we're searching for while not changing any of the other states. Can you guys think of a gate that changes the sign of one of the states while leaving the other states unchanged? Getting some good guesses. Not quite what I'm looking for yet, but good guesses. Ooh, I've gotten 1 or 2. Thank you to Surya and Joe. You guys are right on. What we want is actually a Z gate. So if you remember, so as a reminder, if we are on our, oh, I'm blue. Well, I'll just stay in blue. If we're on our block sphere, and we're in our 0 state, and we apply an x gate, we're going to go, this is our x-axis, this is our y-axis, and this is our z-axis. Our x gate will rotate us around our x-axis and put us in the 1 state. So if we are in a superposition of 0 and 1, our x gate is, I guess, if it's going to change the superposition, but it's not just going to flip the sign on it. To flip just the sign, what we want to do is instead, if we're in a superposition state, so we're maybe facing along the y-axis, I guess it doesn't matter which one we choose, and we want to apply, apply a z gate, which I'm going to do in blue because I'm just choosing random colors. This is our z. If this state, let's say, just for like, this is just an example, if we say this is 0 plus 1 over square root 2, I'm not minding my axes, so if these axes are different from what you expect, I'm not being careful with that. This would be 0 minus 1 over root 2. So our z gate actually flips the sign of only our 1 state while maintaining the sign of our 0 state, while the x gate, I guess if you were in a superposition along the y-axis, you could get into the right state, but if you're along the wrong axis, it won't do what you expect, and it's just not it's not how you want to do it, I guess. Although there are always like different ways you can do the same thing, but you might need to still do some kind of phase rotation, and you will end up with some global phases if you do a non-z gate rotation in this case. Yeah, so I want to be clear, like there are often multiple options, but there's a reason we choose one over the other. Yeah, this, because we have our matrix, which is 0, 0, 0, 1, 1, 0, 1, 1. You can see that this will keep the same sign for all of these, and it will flip the sign for this one, which is our Waldo state. So we are making Waldo go to minus Waldo. It's a bit hard to read, like so. So how can we implement this as a gate, or this matrix? Call this a matrix, not a qubit. As a gate, this is actually what's called a controlled Z gate. And as usual, it's the first qubit that sets whether you flip the sign or not. So if you have, I guess it's a bit hard to describe in like a clear way, but actually I'll just write it out, like maybe, so our CZ output, let me write A and B first. We have our A, our B, and our CZ output. So it stands for controlled Z. If A is 0 and B is 0, it does nothing. I guess I'll just say it's, well, yeah, I'll say it's 0. If A is 0 and B is 1, A is the control bit, so this still does nothing, and it just keeps it as 1. If A is 1 and B is 0, it would flip the bit, but because it's 0, you can't add any phase to 0, so it just maintains the 0. And then if A is 1 and B is 1, you can flip the sign of B, and so B becomes -1. And that's what this matrix is showing. This is a bit like simplified, I guess, because we do have now like 3 axes, like this phase term that I'm kind of ignoring and just treating the options as 0 or 1. That's not totally true. This will just flip the sign. But if you take only these 4 options, this is what you'll get out. Cool. So If we apply this oracle on the state vector at the end of step 1, which is 1/2, 1, 1, 1, 1, we can work through this. And it's pretty straightforward, actually, to figure out what our output is. Can anyone tell me, actually, what our output is going to be for this? What should I write right here? Thank you, Surya and Fahim and Tomas and Alex. You guys are very quick. I'm very impressed that you guys remember your matrix multiplication so well. So I know it is like a new topic, and I feel like math is like learning another language. I'm always impressed when people remember like random implementations of another language. This is 1, 1, 1, minus 1. So you can look at this and see you multiply, again, like your first row here by your first column here, your second row, your second column, et cetera, and then sum them all together at the end. So you just end up with a column in the end. So let me make this more of a dot. So this guy is the only one that is affected by the -1 term, and the rest just remain the same. And we can normalize it by our half term. Got a question from Elon. Is the oracle matrix always the same? This is the entire point. That's a very, very good question. It does not always have to be the same. All that it matters is that you get this output out, where it flips the correct location. So if Waldo was hanging out up here instead, then you'd want your -1 to be there. So you need to have some way of implementing an oracle that will flip the correct bit. And if you have some kind of search like information, then that will allow you to apply the right function to that information. So it does not actually mean you need to know where he is in order to make the oracle, because there will be some unique, and like if every entry of your data set is unique and there aren't multiple options, then there will only be one state vector that will interfere with your oracle in the right way, because we are implementing like a more like, I guess, like analog implementation. You could also think of it as running like an exclusive OR on a data set that's all ones and zeros. If you exclusive OR it with zeros and your data set is all zeros except for a single one, then everything is going to fail your exclusive OR and give you zeros out, except for the one that's the one. I know it's a bit of a like annoying descriptor, but like for example, if you had something like 0, 0, 0, 1, which would be like the same as what we have here, and we exclusive OR it, or that's our tensor product. We exclusive OR it with 0, 0, 0, 0. We're going to end up with 0, 0, 0, 1 out. So quantum algorithms allow us to do the same kind of exclusive OR effect, but with arbitrary phases rather than just zeros and ones. So we are kind of using the unique quantum mechanicalness of our system to allow our oracle to adapt to whatever we're putting in. But in this case, we have chosen, we know where we think Waldo is, so we can kind of simulate the behavior. But in general, you do need to like run this on like a quantum computer to get the right results. So yeah, cool. So, this doesn't actually write it out. Well, we wrote it out. And so what we've done is we flipped the sign or the phase of Waldo's state. And now that he stands out from the crowd, we can find him much more easily. He's not just at 25%, I guess he still is. but he's actually like the negative square root of 25%, rather than just 25%. So now the next step, this is actually step 3, is applying Grover's diffusion operator, or I guess it's still part of step 2. It's still part of our for loop. But at the end of our previous step, we have this state where we just flipped our Waldo state. And in the end, we'd like to have just 0, 0, 0, 1. How do we make this transformation? Well, we want to create a gate that will take the first vector and give us the second. And so when we say a gate, a lot of times we just mean, or we can just mean a unitary. So like a unitary, like a U gate could actually be something like a Hadamard gate, and then a Z gate, and then a Hadamard gate. And this is still a unitary. You could just make a single gate that did this, but as far as what we're actually applying to the gates, or applying to the qubits, we describe it more as this one. This is more physical, and this is mathematical. I don't know why I can't write today. I'm sorry if like any of my writing is like not easy to read. I'm just gonna write mathy here. Yeah, there is like you can demonstrate, like you can prove that you can deconstruct any unitary into a sequence of gates. But if you actually want to like feasibly run that sequence of gates on your quantum computer, you should probably know what they are and whether they're like reasonable. So this is Grover's diffusion operator. We're not proving how we got there, but we'll show you the deconstruction of this unitary matrix to show what gates you can use for this. And you can, so I guess I'm gonna show the gates in a second. But all this is doing is applying this is a general operator that does not just give a certain output given a certain input. This is a general thing that applies to everything, and it will amplify the negative sign term. And you can see that when we apply this to our state after step 2. I guess I'll just write it out here. So if we multiply through all of these, so we're going to multiply 1 by -1, 1 by 1, 1 by 1, and then -1 by 1, and then we add them all together. This gives us, I'll start writing it out. This is -1 times 1 plus 1 times 1. Actually, I'll do little crosses, plus 1 times 1 plus 1 times -1. I'm sorry if this is like hard to read. It's a lot of terms. We can do the same thing for every line. So this guy gives us, let me write it out like this. It's a little easier to read. I feel like I have just a lot of lines and it doesn't look very readable. Cool. This is 1 times 1, 1 times -1, plus 1 times 1, plus -1 times 1. I'm kind of doing like arbitrary directions. And the same thing for the fourth line. Times 1, plus 1 times -1, plus 1 times 1. And then the final most important line, 1 times 1, plus 1 times 1, plus 1 times 1, plus -1 times -1. So this will give us, normalized by 1/2, -1 here, plus 1 plus 1 plus -1. So that's 0, because we have -1 plus 1 is 0, plus 1 is 1, -1 is 0. Same thing with this line, 1 plus -1 plus 1 plus -1, 0. 1 plus 1 plus -1 plus -1. Yeah, there should be a minus here. Is 0. And then 1 plus 1 plus 1 plus 1. This is actually all like whatever. What am I saying? This is this, because it's minus times minus, we get a plus, and this gives you a 4. And I think my normalization is off because this should actually be 1/4, not 1/2, because we have 1/2 times 1/2. So this should be 1/4. This will give us 1/4, and this gives you 0, 0, 0, 1, which is our Waldo state. Yay, we did it. We've done the math. It's a lot easier to do on a computer, but I think it's nice to see it kind of written out once, in like an explicit like form. So when we want to implement Grover's operator as a bunch of gates, so we have our unitary, we want to break it up into gates. This is the answer. Deconstructing that matrix into this set of different matrices is super annoying. This actually is Hadamard tensor product with Hadamard, Z tensor product with Z, then like a controlled Z. Yeah, that's not a, oop, that is not an easy to see Z. And then Hadamard tensor product Hadamard. This is like quite annoying, but in the end, it does work out to be your Grover's diffusion operator. And you can do this math. It will probably take you like an hour, but you can totally do it, and you can see that it works out to the correct matrix. So then after we've done this diffusion operator, we've demonstrated that we get the right answer. We've shown that we can deconstruct this unitary into a bunch of gates. Then we measure our qubits to find our final state. So if Waldo was found successfully, what should the final state be? Well, I guess I didn't write it down. Does anyone know, I guess, what the final state should be? Does anyone remember the state vector that we're looking for? It's our 2-qubit state. We've gotten 2 answers, and I love when the answers are different but exactly equivalent. Thank you, Tomas and Joe and Anantha Krishna. You guys are all down in Syria. The final state we expect to get is our 1-1 state, which is our Waldo state, which is 0, 0, 0, 1, just like we found. So this is our full Grover circuit. The first step is our Hadamard gates. This is making our superposition. Let me write that out. And specifically, it's an equal superposition of all states. Second step is our oracle. In this case, it's a CZ. This is like selecting or like interfering, I guess. Selecting our state. Then we have our diffusion operator, which is amplifying our state. And then we have our measurement, which is just measuring it. So you can think of this process as kind of initializing to everything has equal likelihood. Then we select or interfere our states with like our oracle function, and that selects down and like specifically marks the correct state by flipping its amplitude. And then we amplify the amplitude of that state so that we can actually read it out. And then we read it out. And this works very, very well. And so to demonstrate just how well this works, I know we are at time. This will be uploaded to YouTube, and you guys can watch it on your own time. We also have another version uploaded by Corbin, depending on which version you'd prefer to watch. But we're going to now switch to coding. to actually show how we do Grover's algorithm. So with that, let me swap to our code. If I can find where it is open. Oh, I have the wrong thing open. Okay, cool. You guys can see this hopefully. And I promise I won't be offended if you must go. I know this is a particularly long lab compared to usual, but I think we've covered the important parts of like the theory. So you guys are all good on the like mathematical theory for this, and you can totally work this on your own time if you need to. Cool. So now, this is just giving a brief run through again of what we kind of went through in the slides. We're going to be doing an unstructured search again, so we have no way of telling which state is which. As far as like what we know, like the oracle can tell because the oracle can interfere our states. That's kind of the special thing the oracle has that we don't, as it has special ways of marking different states from other states. Oh, I got a question from Syria. Is there a quantum search algorithm for sorted databases that is faster than binary search? And is there a quantum sort algorithm? I don't know off the top of my head. I feel like I should probably, well, I don't know. I don't work on quantum algorithms, so unfortunately I'm not an expert in that area. There are a lot of quantum algorithms kind of popping out of the woodwork all the time. But a lot of things you can also create classical analogs for. So I'm not actually 100% on that. Sorting is a bit difficult, I guess, because you have to mark each state somehow. And I don't know if you get the same level of quantum advantage for sort. I know you can get a big quantum advantage for pathfinding, but I don't know about sort. So definitely, I can look it up and inform you of my findings next lab. Cool. So again, we'll be doing our unstructured unstructured search. And to implement the Grover circuit we want, we're going to import everything we need. So we're going to use Matplotlib's pyplot library, NumPy for our numerics, Qiskit, import it as Q as usual. I'm going to take the least busy provider, like the least busy quantum computer available to us, and then the plot histogram function from our visualization. So make sure to run this and make sure the star goes away before you run anything else. So now that's run. And remember that we want to implement the following 3 steps, like we noted. So we have our superposition step, where we apply a Hadamard gate to every single qubit. We have our oracle step, where we just apply a CZ gate in this case, because we like that's how, I guess the oracle is kind of how we're feeding in the information of what we're looking for. But in this case, we know where it is. Normally, like we would just feed it in, the oracle would just tell us the right answer. We have our Grover diffusion operators, which is just a Hadamard, a Z, a CZ, and then Hadamard again. And then finally, we have our measurement at the end. So to start out, we're going to define an initialization function where we just apply a Hadamard gate to each of the 2 qubits. So we're going to apply Hadamard to our 0 qubit and our 1 qubit, and then we're going to add a barrier just to visualize it and separate it from the rest. So I'll run that. We can then run our function actually to see if we did it correctly. So we're going to first initialize a quantum circuit, which is q.quantum circuit. So this is our Qiskit library, and we're going to make a 2 qubit circuit. And then we'll run the initialize function, passing in the circuit we just created, and we'll draw it using Matplotlib. So that's all we're doing here. And this is our Hadamard gates on each qubit, and then our barrier. We want to implement this oracle matrix, which is our control Z gate. So we can just apply our oracle for that. So the oracle for the 1, 1 state is the CZ gate, with the 0 qubit being our control bit and the 1 qubit being our like logical bit. And then we'll add another barrier just to make it clear. So we'll initialize this function. And this is our specific oracle for Waldo being in the 4th position or in the 3 state. So we'll do this again, calling our oracle function we just defined, passing in our Grover circuit, and we'll add it to that. And we'll run this, and you can see it right below, adding this part of the circuit. Next, we want to apply the Grover diffusion operator, and the matrix for that is this, which can be decomposed into this gate sequence. And sorry, I'm going kind of just running through this rather than letting you guys code along. Because of time, I don't want to go on too long, but definitely like work through it on your own time. So all we're going to do for this is apply a Hadamard gate to both the 0 qubit and the 1 qubit, apply a Z gate to the 0 qubit and the 1 qubit, apply a CZ gate with the 1 qubit being controlled by the 0 qubit, and then apply the Hadamard gate on the 0 qubit and the 1 qubit again. And then we'll add a barrier at the end, and this will create this unitary, this whole sequence. So this is our U sub G, so this is our Grover unitary. We'll run that, and then we'll call this function again on our Grover circuit. And you can see this is what it looks like. And then finally, we want to measure our qubits. And so in this case, we're going to actually use a special function rather than measuring each qubit individually. We're just going to use measure underscore all, which is a nice built-in function to Qiskit. And this will measure all the qubits we've initialized for our circuit. So that's what we're doing here. This is what we get. So then we can simulate this circuit, and we're going to use the QASM simulator. As usual, we're going to do like the normal kind of, like we're going to pass in our Grover circuit with the backend we've defined as the QASM simulator, and using 1,024 shots, we'll get our results, we'll get our counts from results, and then plot the histogram for these counts. So this is the same sequence we've done for pretty much everything we've programmed in Qiskit. So we'll run that, and you can see we get 100% in the 1-1 state. We can also run this on real devices. So you can load your account information, get the provider you want, and then choose the least busy simulator. In this case, I'm not going to run this because it's going to take a few hours to get access to one, but I ran this on Lima earlier. And then we can run our circuit on the least busy backend. So that's all we're doing here, is we are first transpiling it. So we have to convert our circuit into a sequence of gates that can actually be run on this particular computer. So we have to pass in the right backend, and we can optimize it to some certain level. We've chosen 3. That's you can look up how this optimization works, but it's a little outside of the scope of the course. We can assemble our transpiled circuit as a quantum object, and we can run it on our backend, and then we can monitor it. And this will just like give us updates on the status as it runs. So it eventually gave us the job has successfully run. It took a little while, maybe a few hours. And then we can pull the results from the job that we just ran. So the this gets stored in results, and then we get the counts, plot the histogram, kind of the usual sequence we do. And you can see that we get about 89.2% Waldo state, and then I guess like 10.8% other states. Does anyone know why we get a difference between this plot and the one in the simulation? You guys are so quick with this. Thank you, Surya and Jade and Nantha Krishna and Naveed. Yeah, you guys, feel like you're very like familiar with noise for people that don't like work on like sensitive systems. I feel like you learn very quickly that noise will destroy everything that you love when you work in a lab. But I'm impressed that you guys like are just like, ah, yes, this is clearly noise in the system. It's errors that are building up. Um, so we have some small likelihood, 0.7% that we end up in the zero state. That's the ground state. So um, for both qubits. So we'd have to flip both qubits unintentionally rather than just one. So it's less likely we'd end up there. We have about 6% chance we end up in the 0, 1 state. So qubit 1 has flipped, but qubit 0 hasn't. And we have about a 4% chance we end up in the 1, 0 state. So qubit 1 has flipped, but qubit 0 has not. So it kind of makes sense that we end up with primarily one of these two states, in much less likelihood this state when we get errors in our circuit. So with that, that is the required content for the lab. I only went 10 minutes over. I wish I possibly could have gone through like showing each line of code, but it is just adding in the circuits that we have written, and I hopefully demonstrated that is that those circuits get you the results you want. So I'm going to stop sharing the screen and again switch back to the slides, just for some final notes. Oh, cool, cool. So, and if there's any questions also on what we just did, I can annotate a lot more easily on the slides than I can in the quantum experience. So let me know if there are any questions on that. It was just implementing the math we already showed. And hopefully everything seemed pretty familiar. But while you guys think, I will try to move through the key takeaways for the sake of time. We didn't demonstrate this, but it is demonstrated a little bit more in the extra content in the notebook that was sent out on Canvas. But Grover's search algorithm, you can show has a complexity of O of square root n. So that means that you have to run the Oracle Grover diffusion square root n times, depending on what your n is. So in this case, I guess for 2 qubits, you only have to run it once actually. But for larger circuits, you need to run it square root n times. And this is our 3 steps for Grover's algorithm. It's our superposition, our like interference / selection, and then amplification. So I'd say like interference plus amplification here, and then superposition here. And this is using a superposition as well as interference as usual to create a more efficient algorithm than you can achieve classically. So it's kind of a key thing to realize is all these algorithms are using these superposition states and these probability amplitudes to give us an interference effect that allows us to do something more efficiently than a classical algorithm can do. So with that, I will start the post-lab Zoom feedback. You guys can fill it out before you go. And I do have optional content on the Oracle that I'll go through. If you're interested, you can also watch it on your own time because it will be uploaded. So hopefully this made some sense. I know I've lost a lot of people because I am over time, but I appreciate those who stay and those who watch whenever it is more convenient for them also. Okay, so we have some further reading and resources as usual. I really like Scott Aronson's notes on oracles. These are really, really good. And then we also have some other useful pages. These will be sent out. And then we have our optional content on the oracle. I don't know how helpful this will actually be, but but hopefully can give you a slightly different perspective on oracles. Um, so to use an oracle, our goal is really just to reframe how we solve the problem, where we're like the oracle is pretty much solving the inverse problem. It's going to give us the output we want, given any input. Um, so our regular approach is, if I have a list of n entries, how do I find where the entry I'm looking for is? How do I do this? The oracle approach, we don't have to find it. We've already found it. The oracle has found it for us. It's solved the problem already, but we want to figure out which entry it has marked, rather than actually finding this entry. So this is why we say we're doing like an amplification rather than a search sometimes. So in this case, we have the entry we're looking for, which we've marked in this case, but realistically, this should be, I guess, more blue. Like if this was blue, we're just like looking for this. It's secretly orange, but we don't actually know. It's not marked. It looks very, very blue. Meanwhile, the one the oracle marks is pretty easy to find comparatively because it has a different amplitude than the rest. So we have noted a bit about this for like designing oracles. For now, we're not going to worry about who made this oracle and how they were made. They just were given as a gift to us, which has been quite convenient. So this is our given. And all we're going to focus on, and kind of, I guess, the important part of these algorithms is to figure out which state it marks. So all you have to prove about an oracle, using an oracle in a computer science problem, is that an oracle exists that will do the thing that you want it to do. So we want to like prove oracle exists, but we don't actually need to do anything as far as implementing this oracle. So any oracle that exists that will do what we want is perfectly sufficient. We don't need to actually like demonstrate all the possible oracles we can use. For both Deutsch-Jose and Grover's, we can discuss which gates the oracle will implement if we know which state the oracle marks. So if we know that we want the oracle to mark the 1, 1 state, we know which gate we need for that. If we want it to mark the 0, 1 state, we can create a gate that does that, or a sequence of gates that does that. But it is like a bit of an if statement, depending on what it is. And there's many different ways you can implement the oracle for each of these possible states. So in this case, how does the oracle know where to place the minus sign? Well, we've kind of given it which what matrix it's going to use. It will just place the minus sign where that matrix tells it. But there is some step that we're not really covering, which is how the oracle actually decides which of these matrices to use. If we gave it 4 possible options, it has to check which one it should use. So we do have some open questions that hopefully like we will maybe make a little bit more clear, but it isn't something that I guess is a high priority because it is like I don't think I have a like super in-depth understanding of oracles. I can use them, I can identify them, I can tell what I want an oracle to do, but can I design one? Probably not, because it's an active research area. So if you can't design one, I can't design one either. I'm sure I can put together something that's going to be very inefficient that might do what I want, but it's not necessarily a good oracle. So our open questions are, how do we design the oracle without knowing which function it actually implements? This is required for any practical implementation. It will always be doing some sequence of gates, but we could kind of fake it and say, well, if it's this state, do these gates. If it's this state, do these gates. And that's kind of what we did last week. That is a perfectly mathematically equivalent way of doing it, but physically you would want a more efficient way to do it. We also want to note for an oracle, we like if we're trying to do a search, we want the state we're looking for to look different than the rest of the states. So this is our needle in a haystack kind of problem, but we don't actually have to know how to create that needle in a haystack oracle. We've done an example for one state we're looking for, and you can think of ways to mark the 0, 1 state or the 0, 0 state instead. Like if you want to mark the 0, 0 state, what you want is this matrix for Waldo is equal to 0, 0. Just want to flip different states depending on what state Waldo is. So you could create a bunch of if statements in Qiskit and implement the different circuits for different things. So if it was instead like this Waldo is equal to 0, 1, then instead like this guy would be negative. And that's how it goes for each of them. You could definitely do it in a kind of dumb logic kind of way, but there are nicer ways to design oracles that are a little bit more physical as well. So with that, that is the end of the material for today. Are there any questions? The material we covered. Okay. Well, if there aren't any further questions, thank you all so much for attending lab this week. I hope you have a wonderful spring break for the next 2 weeks, and I guess I will see you in 3 weeks for the remainder of the Intro to Quantum Computing course. But we are in the home stretch. We will be finishing up very soon. And if you have any questions about the certificates and everything, please email student@qubitbyqubit.com or .org. I don't remember. The email that is all over Canvas, etc. They can help you with those kind of logistical things. Unfortunately, I can't because I am a humble TA. They hire me to do math. But yeah, I have no other answers than what they do, unfortunately. Yeah, cool. Yeah, thank you everyone. Have a wonderful week and definitely post any further questions on Piazza and hopefully we can answer them there. Okay, bye.